feel like I'm in a Cheech and Chong movie. Section 7.2, the graphs of polar equations. In section 7.1, we talked about how graphing ordered pairs that were polar coordinates. We use the polar graph paper, and we are able to plot the points using the polar distance r and the polar angle theta. We also mentioned that there's more than one way to indicate a set of coordinates that would indicate for a particular point. Now what we're going to do is we're going to go to polar equations in terms of r and theta, and we're going to graph those just like we used to graph back when we were learning new graphs in algebra. We learned how to graph a line or how to graph a parabola. We would plot points. We would make a t-chart and we would plot points until we got to a point, no pun intended, that we understood what we were doing and we knew some of the similarities and some of the things to look for so that we could maybe jump right to a graph. Well, because these polar equations are so different than what we're used to using, my suggestion is you make a table of values, and I wrote down lots and lots of values. Now, you can make your t-chart vertical like this with r and theta, or you can make it horizontal like the example that I had down here. I made it horizontal so that it would fit nicely on the board here. So what we're going to do to graph polar equations is make a table of values. Now, when I say make a table of values, we don't pick r and then solve for theta. We're going to pick thetas, and then we're going to plug them in and find the corresponding r values that go with them, and then we're going to plot those points on polar graph paper, and we're going to draw a smooth curve through these points as our theta increases. This is referred to sometimes as the orientation of the graph. So we'll see this with an example or two here coming up, but remember, because these are different equations, you're not going to be 100% sure what your graph's going to look like, so a few points might not be enough. You might have to graph several points. And as you can see in the example that I have down here, look at the table of values. I picked every multiple of 30 and every multiple of 45, or every multiple, I should say, of pi over 6 and pi over 4 between 0 and 2 pi, because we're going to be using trig functions in 90% of these. What we want to do here is we want to use angles that we are easily able to find, plus the fact it's periodic. So going from 0 to pi, if it involves tangent or cotangent, going from 0 to 2 pi, if it involves sine or cosine, or actually secant or cosecant as well, will give us all the points we need. Beyond that, then we start repeating values. And when you want to read this, it says, in the polar equation is easy to convert to a rectangular equation. It may be more convenient to graph it in rectangular form. For example, the last two equations that we looked at in the last, or two of the last, I should say, equations that we looked at in the last video were r equals a constant or theta equals a constant. Well, we know those are circles and those are lines. So we can graph those maybe a little bit more readily. We just convert it into rectangular form. But when that asks for you to graph using polar coordinates, I do not want you just to run to Desmos or run to a graphing calculator to do the work for you. You use these to check your work. I'm going to want to see points that are plotted with your curve drawn. And remember, it's going to be a smooth curve. It's not connect the dots with a bunch of line segments. So here's my first example. Y equals negative 4 cosine of theta. Oh, good Lord, I wrote down y and nobody said anything about it. I should have heard you guys from the camera there. R equals negative 4 cosine theta. That's much better. So that I have my r and my theta, and I did not pick r's. I picked my thetas first. I just, for convenience sake, I went ahead and wrote them all down, and then I substituted these in one at a time into here to find the corresponding r. For example, if I just do a simple one, if I take pi, the cosine of pi, put pi in here, the cosine of pi is negative 1. Negative 4 times negative 1 gives me an r value of positive 4. Remember, if the r is negative, we're going to go in the exact opposite direction that the angle tells us. So now we're ready to graph some points. And as you'll see, there are patterns. I mean, even if you just look at these numbers, there are patterns. Also, it is convenient to remember that the square root of 3 is about 1.7, and the square root of 2 is about 1.4. So this value here, negative 2 times the square root of 3, would be about, negative 3.4. This would be about negative 2.8. So that you can use your approximation skills to plot these points. And 2.8, and negative 2.8, and negative 3.4. Now I'm not going to just graph them haphazardly. I'm going to graph them in order as my angles get bigger. That way I know how to draw my curve, because that's what determines the graph's orientation. All right, so now I need to bring the graph paper up. So let me set that down, as my graph paper is just a little bit heavier than yours. All right. I have this fear that this is going to fall down on top of me or somebody else, but for right now, this is going to have to do. Okay, here we go. Our angle is 0. Our polar distance is negative 4. Well, this is left over. There we go. Now that's better. Let's see, what's the biggest it gets? It gets to be about a 4. 1, 2, 3, 4, 5, 6, 7, 8. Maybe this time what we'll do is we'll make this equal to 1. That way I have a bigger graph, and it's not so small, especially if you're using the polar graph paper that I provided, because the grids are a little smaller. If you expand it a little bit there so you get a bigger shape, and let's see what happens when we graph this. Negative 4 is 0. 0 is this way. So negative 4 would be in the exact opposite direction. 1, 2, 3, 4. There's my first point. Negative, or I should say negative 3.4, approximately negative 3.4, and pi over 6. Well, pi over 6 is in this direction, but if I'm going to go in the opposite direction, negative 3.4 would come out this way. So this is negative 3 here. So negative 3.4 would be about here, I would guess. All right, next one up is pi over 4 for the angle, and the r is negative 2 squared roots of 2, or about negative 2.8. So pi over 4 is this way, going in the exact opposite direction. 2.8 would be about here. Let's make sure. 1, 2. Uh-oh, did I mess up? 1, 2, no, 2.8. Doubled up there. And let's see what's next. Negative 2 pi over 3. Pi over 3 is in this direction, but negative 2 would come back this way. 1, 2 would be right here. So some kind of a curve, looking at those points there. And then we get to 0 pi over 2. Well, it doesn't matter what the angle is. If the polar distance is 0, you're at the pole right here. So I'll make that nice and big. Well, no, kind of round. Let's see. 2 square roots, 2 pi over 3. So in this case, 2 pi over 3, 2 pi over 3 would be this way, and it's 2. 1, 2, right here. Then it's 2.8 and 3 pi over 4. 2.8, there's 2.8 right about here approximately. And then, let's see, about 3.4. Well, these are not lined up very well, but it goes here with this angle here. So that's 5 pi over 6. 3.4, there's 3. So 3.4 would be about here. And then I'm at 4 pi. Pi is this way. 4 puts me right back on the point. Well, I don't know if you can see it very well. I'm looking at the screen to see what you guys are seeing. And, well, of course, I have this point left over from a previous day. I'm looking at what looks like kind of a circle here. Let's see what the rest of these points give us. So now I'm at 7 pi over 6, which is down this way, and my polar distance is 3.4. Well, that's right here. Hey, wait a second. I think we're just going to go right back over all the points that we just grabbed. 2.8, 2, 0, right back there. Okay, 5 pi over 3 would be this way, but it's negative 2. Yep, it looks like I'm going right back over the same points. All right, now that can happen. I don't know if it's going to happen. until I actually started plotting points. As it turned out, I did not need all those extra points, but you never know when you need them and when you don't need them, and even when you know, you never know. So make sure that you create that table of values, and let's see. I'm going to try to make this starting here and doing the orientation thing I was telling you about. Oh, that's a pathetic circle. Did I go out too far? 1, 2, 3, 4. That's 4. I just have a terrible circle there because I suspect this is a circle. You can never tell by my graph. Looks like a, I don't know, it looks more like an ellipse than a circle. Let's see what happens here. If I was to take this guy right here, and I'm going to have to move my graph here, or maybe I can just erase some of this up here. Let's see what happens if we convert this into rectangular form. I'm going to multiply both sides by r. Let's see, cosine of theta. This is going to be the plus or minus the square root of x squared plus y squared squared, because that's what r is, equals, and that's x, so that's negative 4x. So I have x squared plus y squared equals negative 4x. If I subtract, or actually add 4x to both sides, and then complete the square, I add 4, I'm going to have x plus 2 quantity squared plus y squared equals 4. So this is a circle with center at negative 2, 0, and radius 2. Well, let's see. This is kind of like the x-axis here. There's the center, and the radius is 2. Even though I didn't draw worth a darn, I think that's my circle. I think I matches up okay. So that's a good way to check along with, again, you could use the graphing calculator or even Desmos, because they will graph polar coordinates. So we need to do something else here with some graphing, and one of the things that we need to look at, and perhaps we could have used here, is the idea of symmetry, because I can see that I have symmetry here with respect to the polar axis. So we'll need to look at for some symmetry tests in the next video.